Good afternoon. I hope I'm audible, right?
Yes, sir.
Okay, good. So, welcome back from the short spring break. I know many of you have been working through this break also, and some probably went for a little vacation. I hope you all are good. Uh, Now, we will start on the next module. We have talked about the software development life cycle, the different aspects of it, and different you know different models for SDLC, and try to see what are the relationships and how the models have evolved over a period of time and what are the practices at present. uh, in parallel, we have been working on the assignment 3, and you'll soon get assignment 4 also. And I'm sure you have seen a lot of design clarifications questions that arose, which is a very typical scenario that happens often in the actual process as well. Of course, unfortunately, in most cases in real life, on the customer side, you will not have someone like me giving you so clear answers. But this is how you start learning. Now, in this process, obviously, we have taken the I mean, we have had to go through the process of modeling various concepts and their behaviors in the system. Like, so we decided how to model a station, how to model the railways, how to model booking classes, and so on and so forth. And we did come to that by just directly analyzing the specification, and we kind of took a shortcut directly to go into a kind of high level design, and which we detail out in terms of the low level design in terms of class components and class interfaces. Now, what we will try to look at the next module in a more structured way is a very well accepted framework for representing models from variety of aspects that they can actually influence the whole process of software design and subsequent implementation. So let me go to the first part of the presentation. This is, I hope the slide is visible. Is it visible? Please confirm.
Yes, sir.
Yes, sir.
Okay. Thank you. Thank you. So we will talk very specifically on modeling for software design, because models are the most important things, and we will use the framework, or we will introduce you we'll get introduced to the framework of UML, Unified Modeling Language, which is kind of a bridge between what is written by the customer in a kind of a non-structured or semi-structured manner into uh, certain graphical language, which takes away the ambiguity in the natural language description and tries to make it in a form which will be equally understandable, or which will not have the semantic ambiguity of natural language, and will make it clearer for our subsequent high level design. So this is where we start. So this is kind of what we will go through. So I'll just today I'll introduce you to the aspects of modeling, and you'll see that though we have not formally talked about this earlier in the course, but in course of our long discussions in various aspects of C++ language features and what we can do, what object orientation can bring, you have actually got exposed to these concepts already to a pretty good extent. And then we will get into the specific UML syntax and semantics, and study the role of various UML diagrams in the context of different SDLC stages, like requirement specification, analysis, and design. Beyond that, it gets into the actual, code cutting, which is goes beyond UML and so on. We will talk a little bit about pitfalls and workaround, and touch upon UML 2.0. Actually, maybe we will do more of UML 2.0 also. So the question is, what is a model and why do we need model? Now, naturally, finally, the customer is interested in a working software. When it comes down to it, the real point of software development is cutting the code. Diagrams are good, but they're diagrams, they're pictures anyway. But models, as you can see, just to talk generically, is whatever you have studied so far. In everything, you had a model. You had a model which was probably, in many cases, theoretically derived through mathematical means, or kind of postulated and then kind of visualized in that way, and so on. For example, in physics, you have time distance equation. U is the initial velocity, A is the acceleration, T is the time elapsed, and S is the distance traversed. We say that S is equal to U times T plus half A T squared. This is actually a model. So what will happen in real life will, a train will start at a certain speed, accelerate at a certain rate, and over a period of time will cover a distance. This is what is happening in reality, but through this equation, we can actually predict what will happen. We can actually model what is happening. So that's kind of the sense of a model. So in this kind of a model, we use different principles of physics and do a mathematical formulation to get to the model. Or in chemistry, you have learned about different valency bond structure. Now, this is not a model in the sense that it physically actually is, laid out in that way, but it's kind of from the behavior of different chemical elements, as well as the compounds that formed of them, then their affinity to bind together is conceptualized in terms of a model which we find easy to understand, and which reasoning on which can actually replicate in terms of things that happen in the real world. Mathematics, of course, is full of models. Geography, you have maps, projections. You have done electrical circuits like Kirchhoff's loop equations, time series for signals. Transistors have active model, passive model. In building design, you have drawings, finite element models, and so on and so forth. I mean, wherever you have to, solve problems, you need to represent the real world in terms of certain mathematical, graphical, or intuitional representations, which on one side take away the ambiguity of the general description of the physical world, and on the other side allows you to perform operations on the model which will get replicated in reality in the physical system, right? So that's the basic need of the model. Now, naturally, real systems may not be available to do things. It may not be accessible. It may not be affordable. So models come handy in that. The other reason that we go for modeling is, finally, every design, every system is done by a human being, someone like you and me. And our cognitive mechanism is somewhat limited. We are limited by having a long-term memory where we retain, few details about something that happened or something that we experienced over a long period of time. We don't remember every detail, but we remember certain details which kind of has created impression on us, but we retain that for a long period of time. We call that a long-term memory. And vis-a-vis, we have a short-term memory where we have a lot more details, but we can remember that for a short period of time only. So you can see that, based on what actually happened, if you say that that is the reality, that is the real world, and what we retain in our memory, there is a modeling that goes on. So in terms of long-term memory, the memory model selectively removes details and creates an abstraction only that we retain. In terms of short-term memory, it also creates abstraction, but that abstraction can be more detailed. The other factor I'm sorry. The other factor, which is critical in human cognition mechanism, is the limitation of how many entities we can track in our mind at the same time. Several experiments have gone into it, and it is kind of now established that a normal human being has ability to track only up to 7 entities. That does not mean that everybody can do that. I'm sure many of you would be able to do more than that. I would, at my age, would probably be able to do 5 entities, track 5 entities in my mind at a time. And there are people like Elon Musk who will probably be able to do 15, 20, whatever. But the fact is that there is a significant limitation in terms of about 7 entities that we can track. So if the matter of details in the real world goes beyond 7, or say 5, 6, beyond 5, 6 itself, then we start getting confused. We start losing track of what's going on. So we need to create models as abstractions that can help track this complexity. So models, as we see, have two primary roles. One is to represent the real world in an appropriate way, and the other is to make the uh, tracking management of the complexity feasible for human mind. Right. So these are the two things we are primarily going through. For example, if we think in terms of programs, a small program has a few variables, and without taking recourse to any principles, object orientation, encapsulation, or anything, you can easily remember the variables, track what's going on, build up the logic, possibly debug it effectively, and so on. But as the number of independent variables in the program keep increasing, it quickly exceeds the grasping power of individual, and it requires an unduly large effort to master the problem because it has gone beyond that limit of 6, 7, which we can actually mentally track. So that is where it becomes important to manage the complexity. That is where it becomes important to have different kinds of abstraction. So if we have to, if we put a machine in our role, if the machine could be writing or generating a program, the slope of this curve would be linear. For us, it goes linear up to 5, 6 independent variables. Beyond that, it starts flattening off, and maybe beyond 10, 15, for most of us, it will become completely flat, that we are not being able to track the rest. Whereas a machine can linearly do that for a very, very long range of independent variable. And so machine have that ability, but humans do not have that ability. But it is a humans who will have to actually do the model, write the code, and implement the system. So there is so kind of you can see the other side of it. For example, when you are in second year, when you come to third year, you will see you will go through compiler construction. You will see that a compiler is a very complex program, but its complexity is managed by the fact that much of the compiler is generated by compiler generating programs. So there are compilers who actually, in which you just specify that this is what the compiler should be, and then the machine can generate a huge compiler. So that's a different way that, and that is possible because machine can work linearly over a largely complex system, but we cannot. So to make this effort versus size curve remain more or less linear over a wide range of parameters, we need the software engineering principles. And those principles are what we have been focusing on all the time, so that we can overcome these, typical limitations of the human cognitive system. So, what are the tools? What are the principles we have at hand? You know both of them by now, but this is just a formal introduction to that. The two important principles are abstraction and decomposition. Abstraction and decomposition. So, what is abstraction? An abstraction is simplifying a problem by omitting unnecessary details. That is, a problem in general has a lot of details. You cannot handle all of that. So you selectively choose details which are important in the context in which you are talking of, or you are interested. So it's only one aspect of the problem is what you choose, and ignore the rest. Ignore the irrelevant details from that aspect. From a different perspective, maybe you will focus your attention to a different aspects and choose the current one and others. And this is called model building. So suppose, just a hypothetical question. Suppose you are asked to develop an overall understanding of some country. You have to okay, make an overall understanding of Rwanda. Right? Now, how do you go about? Would you meet all citizens of the country, visit every house, examine every tree in the country, every building in the country, or so on? Of course not. What would possibly refer to, at least to get started with, is to various types of maps of that country. For example, here you see a map, which is an abstract representation. On the left, you have what is called the kind of political map. It shows you the administrative boundaries created within India for different states, the location of different places, and so on. These boundaries are not factual. These boundaries, say a boundary between Telangana and Andhra Pradesh, is just in our thoughts, right? But we represent that in terms of this map, making a model. So that's a political model. On the other hand, on the right side, you have what is a physical model, which is trying to show certain physical characteristics of the country of India. What is a highland? What is a lowland? What is the slope of lands? What is the land? Where is the water? What is probably a very cold area, and so on. So you are again representing a country, but you are using an abstraction which is very, very different from a political abstraction, right? So you choose the aspect, ignore the others. There could be several others, like there could be a map for your railway network. There could be a map for your population density. There could be a map for your COVID transmission. Of today's time, there could be a map of vaccination coverage. But each one you choose, you are focusing on one aspect primarily and ignoring the rest. Right? So that's the kind of the meaning of the abstraction. So there could be several abstractions on the same problem, and different types of models help understand different aspects of the problem. So some of the common ones, maps we talked about in terms of country or continent. There's physical map, political map, road network, rivers. Similarly, when we do electrical design, we have maps which are we have models which are abstractions, which are schematic. You just do a kind of a three corner sawtooth to represent a resistor. You do a kind of a spring to represent an inductor, a set of parallel plates of equal size to represent a capacitor, parallel plates of unequal size to represent a cell, and so on and so forth. Connect them through connected lines, and you say it's a schematic diagram. Schematic because that's not exactly what exists on your breadboard or on your PCB, but this represents the different electrical components and their connectivities. Whereas at the same time, so you are looking primarily as the electrical connectivity characteristics or the component characteristics that is involved in the electrical design. On the other hand, When you are, say, doing a PCB, you are most interested in doing a layout as to where will you put which component, which register, how will you connect them. It goes even lot deeper and complicated as an abstraction, as a model when you do layout for the integrated circuits. There could be a completely different kind of an abstraction in terms of the timing. I mean, what are the delays in the circuit and so on. So you do one, you focus on that, make an abstraction, a view, which is primarily focused on that. Of course, it will have relationship to others, like timing has relationship to layout, layout has relationships to schematic, and so on and so forth. But primarily, an abstraction or an abstraction view focuses on one primary aspect. Similar things exist for building design, physical design, plan, elevation, water supply network, electrical distribution, switch network, and so on and so forth. So abstraction for complex problem, we often see that a single level of abstraction may be inadequate. And what could work much better is a hierarchy of abstraction. And that's what you have learned very significantly in the principle of inheritance in object-oriented models. So you have a hierarchy of models. One model in one layer is an abstraction of the lower layer, which is more detailed. And you can think of that implementation of the model gets more and more detailed as you go down that hierarchy. Okay, so that was abstraction. The other that you often would need to handle complexity is decomposition. That is, decompose a problem into many small independent parts. Small parts are then taken up one by one and either further decomposed or solved separately if they have become simple and tractable in complexity enough. So the idea is that each small part must be easy to grasp and can be easily solved. The full problem gets solved when all the parts are solved. That's a simple idea of decomposition. So you break. The reason you decompose is as we know, if you have a bunch of sticks, it is difficult if they're tied together to break it. But you take each and every one, you can break it very easily. So you can decompose and solve the problem in an easier manner. Just a allegorical example. Example that you can think of. So while we decompose, we have to be kind of careful that we do not decompose arbitrarily. That may not help. The decomposed part must be more or less independent of each other, and they together should build the whole. So, for example, we understand a book better when the contents are organized into independent chapters. If there were no chapters, just the entire book, it becomes far more difficult to comprehend. If there were no sections, only chapters, it gets difficult to comprehend. If there were no paragraphs, it is the same content. But we have created several levels of decomposition going down to, sentences and words and phrases. And if you think of the whole organization of language comprehension is a hierarchy of decomposition that you can have so that things do not get mixed up. So you decompose a whole into parts, decompose it part into subpart, subpart into subpart, and go on till you have something which is tractable. So that's kind of what you have in terms of a decomposition hierarchy. This is what we are saying is also a hierarchy, but you get more and more in the decomposed form. So books have chapters, chapters have sections, sections have paragraphs, paragraphs have sentences, sentences have words, words have letters, and so on and so forth. Cars have engines, engines have pistons and cylinders. Cars also have wheels, they have tires and tubes. The cars have steering, so on and so forth. So that's the decomposition principle. Now, when we bring it to, to the fore, naturally, we get to what we have already discussed in terms of object orientation, which is abstraction hierarchy is a relationship, which is inheritance. Decomposition hierarchy has a relationship. If you have read my clarification on assignment 3, you'll see that I have tried to clarify and give some examples there of this has a relationship, which basically means components. So in terms of later realization has a turns out to be components of an object of a class, and is a hierarchy of classes or objects thereof. So this is abstraction turns out to be very handy in terms of capturing different perspectives that are required, because different perspective may require different kind of models, and good models are necessary for making complex systems more understandable. So with that small introduction, let me just start talking about UML. So the question is, let me switch my presentation here. I'll stop and share a different presentation from this point. I'll share both these presentations with you. I hope this is visible. Okay.
Yes,
Yeah?
sir.
Okay. So this presentation again, like the C++ presentation I shared with you, this presentation is also from another, SWAM NPTEL course that I have. It's on object-oriented analysis and design. So it has a lot of these details. So we will just pick up some parts of it from here. So UML, the Unified Modeling Language, certainly, we have to start with a few questions. Say, let's be on slide 3. So first, we have to answer why UML. Why do we need UML? Second, of course, is what is UML? And we will try to understand that from two angles. One is trying to understand what is UML, and the other is what else related to it should not be confused as being UML, and a little bit of history. And then we'll go into different UML diagrams. It's a collection of diagrams, types of diagrams rather, and the features of various diagrams. Now, why do we use UML? It is a notation for system analysis and design. So in simple terms, given a specification which is in natural language, we are trying to create an equivalent for that in a standardized notation. It is a standard. That is the first and foremost important thing. If you say I'm using UML 1.3 or I'm using UML 2.1, then everybody exactly knows what notation, what nuances you are talking of. So it helps a designer or developer to capture artifacts of software design, all the details. What is the concepts, what is the hierarchy, what is the decomposition, what is the timing, what is the sequence of things to happen, so on and so forth. Why would someone, what are the possible ways to use a software, and so on and so forth. It eliminates the issues of inconsistency and accuracy in software design and analysis. This has to do a lot with ambiguity removal. Natural language has ambiguity, and therefore if I can put it in a standard notation, I make things a lot more consistent and accurate, minimizes vagueness and precision in expression, and facilitates robust communication within teams and with client, because now we have a notation which cannot be interpreted in two different ways. So, and naturally, in terms of what it should be a simple, easily understandable notation. So these are the different reasons for which over a period of time something like UML evolved. So what is it? It provides the user with an expressive modeling language. It's a language to model, and it's highly expressive in nature, because you need to be able to express anything that a specification can have. And see, A specification means any kind of system for the real world, or may not even be for the real world. It may be your fictional world, where maybe you want to model that a human being can fly by himself, herself. So it is something which has to have enough expressive power to handle any kind of specification, construction process, visualization of the model, documentation of the model, and so on. Whatever artifacts your software system may have, it should be expressible in this modeling language. You needed this for construction of different kinds of models. As we said, the same reality may have models of variety of kinds. Yeah, as you saw in the electrical circuits, you have schematic, you have layout, you have timing, you have so many others. So it should be possible to construct different kinds of model in the same modeling language. And we should be able to exchange models. Yeah. So what UML does, it provides a user with a number of ready-to-use core concepts, so that these core concepts have been identified, have been standardized through reviews and experiences of thousands of projects by lakhs and lakhs of developers, so that in a large majority of the projects that you may be handling, you might just get the core concept already available in UML. But it retains its value to handle anything, because it also allows you to extend and specialize the language, the concepts, to fit your requirements. It provides a formal basis for the understanding of the modeling language. That is, it might look as diagrams, but every diagram has a very strict syntax and semantics. Like in a language like C++, it has a strict syntax and semantics. UML, I would say, have even stricter syntax and semantics. So it becomes a meta model in terms of UML class diagram, that you are trying to model something, you represent it as a UML model. So the UML model is by itself a meta model. It's a model for making models, right? So that's what makes it a meta model. And semantics is a part of the official UML documentation that goes with these models. Certainly, UML supports higher level development concepts beyond just, encapsulation of classes, abstractions, and decomposition into parts. It supports higher level concepts like collaborations, like patterns. Patterns are something which I hope I'd be able to talk a little bit more on specifically, particularly design patterns, which tell you that these are kind of situations which repeatedly happen. Therefore, you should have a recurring solution for it. So design patterns are recurring solutions for recurring problems. So one, you have, without this formal introduction, one you have already got introduced to and you are already heavily using in your assignment is singleton. It's a singleton pattern where you have a reason to believe that you have created a class, and that class will have only one object, right? So that's a pattern. And however, flimsy it might sound at the beginning, as you get down to doing a lot of different designs, you find that in a real software, there are several singletons that can happen. It could be a physical singleton like the railways, where you have only one Indian Railways, so not considering the subdivisions in that, of course. Or it could be you are actually creating a class representing a concept, say that of a, let's say, first class travel, AC 3-tier travel, AC 2-tier travel, and so on. These are all concepts. These concepts have properties. They do not have computation. So when you represent them in terms of corresponding classes, they have only one instantiation, which will be used as an attribute, decomposed attribute in some form of booking information, right? So they all become actually singletons. So the pattern helps in a very significant way. Functors we have talked of, they are called command pattern, where the collection of information and execution of the command are separated. So in a function call, collection of information, that is collection of different parameter values, and the execution, that is invoking the function, happens at the same time. Whereas in real life, it doesn't happen that way. You go to a restaurant and your waiter walks up to your table and asks for what you want. So what you specify is an order, right? You look up the menu, or if you're a frequenter, you don't even have to look up the menu. You say, I need a cappuccino without sugar. My friend needs a tea without milk, and so on and so forth. Right? The waiter notes it down. So what you are doing is, if you know look it into abstraction, we are basically collecting the parameters for the order. But the order does not happen at that point of time. The waiter takes your order, records all these parameter values, goes back to the kitchen, and puts up that chit in the queue of order making, preparing it. And then whoever is making the cook, or whoever is making up your order, will pick this up from the queue when the turn comes and actually prepare whatever you have asked for. And then the waiter again gets that stuff back to you. So this is a functor. You are collecting the parameter information in the state of the order. Then you are queuing that order for execution. And then once executed, how does it execute? By invoking the execution method. And once it is executed, you get the effect, right? So this is something, this is called a command pattern, because you are giving a command to do something, and that happens through this model. And whether it's innumerable restaurant examples, to different buying examples, to various places, you'll find that this kind of a pattern actually repeats. So it helps to have a solution for this situation in generality, like we did for singleton. So this is called a command pattern in design pattern. So what we are getting back to UML, UML supports these kind of high level development concepts in terms of collaboration, patterns, components, and so on. And finally, last but not the least, is it integrates best practices. I've been talking from day one that software engineering is, or engineering is, about best practices. And software still is not construction. It remains to be engineering, because we are yet to stabilize, formalize, standardize our practices. UML, it takes one step towards that, because it gives you best practices, because you have, for most situation, a pre-solved solution or pre-solved representation of what you have to do. So this is what UML is. But please remember at the same time that UML does not prescribe a certain process of doing things. You could use it with any kind of SDLC model, or even outside of it. It's not a certain modeling tool. It's just a language, right? It does not give any modeling guidelines. It does not say that you must model in this way. It gives you a variety of features in terms of what you can model, but it does not tell you that this is how you have to model. That is the choice or that is the scope for creativity, that the scope for expertise, there's a scope for maturity that is left to the developer, the designer, so that you can use it in novel ways. And it is not a certain programming language. And you can use UML for any kind of final vehicular language, what you use, whether it is C or it is assembly or it is Ruby or anything. And the dedicated goal of UML, as we all understand in the today's world for software, is openness. Everything is open in UML, nothing hidden. Okay, so this is this is about UML. So just to looking quickly back into history, the history is actually very rich to be covered. The unified modeling language is a primary modeling language to analyze, specify, and design software. the the need for this was felt somewhere around late 80s, and it went into well into 90s, and numerous methodologies, numerous ways of modeling, representing, exchanging were developed. They were subsequently modified based on requirement, refined. Many of these were strong in certain areas and weak in the others. So in the middle of 1990s, uh, Butch, Rumbug, and Jacobson joined forces at Rational Software Corporation and began. I mean, they were each were proponent of certain modeling representation, certain modeling language. So they joined hands together under Rational Software Corporation and began to meld their respective methodologies together to create what would become the first version of UML. And in November 1997, the Object Management Group, OMG, you can look at the website, adopted UML as a standard. And the journey from there on goes on in terms of creating newer and newer, more and more rich version of UML, and the standardization remains in place like it does for C++ or Java or those kind. This is roughly the kind of roadmap that it has come through. So I said these are different Butch 93, OMT2, these are different methods which were primarily unified. So these were a lot of fragmentation, then unification happened. And that's kind of the word unified has a loaded connotation in UML. One is it's called unified because it unified variety of methods for modeling. So it's unified in a natural way. But you could also look at unified modeling language as one which can be used equally in specification phase, as well as analysis phase, as well as design phase. And if you are empowered with certain UML, targeting tools, then even a basic skeleton of your code can get generated from the UML for the first level of implementation stuff, right? So this is this is how UML happened. The unification happened around here naturally at 1.0. Then it was between it was 1.3 which finally created the standardization, and then it started. After standardization, it started getting adopted in a wider way, and lot more of requirements came in, and version 2.x came into being, and kind of it is said to have been industrialized, that is adopted heavily in the industry by around UML 2.5. Right, so that's kind of the brief history of this modeling framework, this unified modeling language, since since 90s till today. So in UML, the UML language comprise various diagrams to capture various aspects of software design. So you have a variety of diagrams. For example, a system may contain a number of classes, many interrelationships between them, So we can group the class diagrams logically to depict one aspect of the system. This aspect is the primary one that you have been doing so far. Creating a singular class diagram is not a solution. If you want all concepts will come into one class diagram, it's stupid. Rather, you should take every class, every concept in terms of a separate class diagram and define their interrelationship. So, station is a class, railways is a class, there are booking classes, first class is a class, sleeper is a class, gender is a class, so on and so forth. Across all diagrams, all components with the same name are considered to refer to the same model item. So how do you interrelate? By name, right? So, and that applies across diagram, because every diagram, every type of diagram is describing a different aspect of the same concept. So how do you relate that these are different aspects of the same concept? By their name or the components. So this is the this is kind of recursive representation. So this is the class diagram of UML's diagram types. So these arrows, you have seen them informally during our discussion on inheritance, are easy relationships, specialization relationships. So these are all easy. So these say that class is a structured diagram, is a UML 2.5 diagram. Object is a class structured diagram, is a UML 2.5 diagram. Similarly, use case diagram is a behavior diagram, which is a UML 2.5 diagram, and so on and so forth. So you can see some of the classes I have shown in black. Some are shown in blue. The black ones are the more frequently used ones. So you can see that the blue ones typically are are at deeper levels of specialization. So like you have state machine diagram, state machine diagram per se, because that's a refinement, just a simple refinement on the way you draw FSMs. You draw states, you draw transitions, you mark the start states, maybe you mark the final states, and so on and so forth. But you can specialize to describe it in a behavioral form. You can specialize it further to describe in terms of certain protocol state machines and so on. So that's the kind of, so what certainly we do not have the time to do all of these diagrams. So what we'll do, we'll pick and choose some important ones, like the use case diagram, like the class diagram, or say the activity diagram, and talk about them so that you can get a flavor for what is in UML. And also, as I said, that we are focusing primarily in the requirements analysis and design phase. So there are diagrams which cover the later phases, like deployment diagram, which actually describe the real world situations in which you have to really deploy your system. So we will, for now, skip those kind of diagrams. Okay. So broadly, as you can see in the last hierarchy, there are broadly two types of diagrams in UML. One is called structural diagrams, which show the static structure of the system, its parts on different abstractions and implementation levels, and how they are related to each other. The elements of a structured diagram represent the meaningful concepts of a system and may include abstract, real world, and implementation concepts as well. Let us go back to slide 10 again. So here we are on slide 10. So we have all of these are the first level class diagram coming in here. object diagram coming in here, package diagram coming in here, but composite structure diagram, which gives you internal structure diagram, which is a lot more details about the composite structure of the system. Network architecture diagram gives you a lot of implementation details. So it is, as we say, it is primarily focused in the three phases of specification, analysis, and design, but it has its feet on deeper down in the SDLC. In contrast to structural diagrams, behavioral diagrams show the dynamic behavior. They show what are the actions, what are the behavior of the objects in the system, which can be described as a series of change that happen to the system over time. So if we again go back to slide 10, you have sequence diagram, which tells you the sequence of events that can happen. You want to do a net banking transfer. What is the sequence of events? First, you have to open the browser. Then you have to launch the portal of the bank. Then you have to log in. Then you have to choose your transfer mechanism. Are you doing intra-bank transfer? Are you doing NEFT transfer? Are you doing RTGS? And so on and so forth. So there's a sequence of things that you do. So the sequence diagram is one. Activity diagram is one, which tells you about these. What are the different activities you do? How do you sequence these activities? You may go deep down into actually defining timing for those. For example, a login to a internet, net banking portal will expire without activity in a certain amount of time. So there is a physical clock-based events involved as well. So if you look on the right side, the behavioral side, it is the dynamics of the system. On the left side, it is the structure of the system. And the dynamics certainly has time as a primary parameter. So those are the very generically, no matter what kind of system you are doing, those are generically the two major aspects on which a system has to be developed. I think I'll stop here before I start taking on specific diagrams and rather go back and take questions if you have any. Yes. Ask me questions.
Sir, is the singleton pattern like heavily used in C++ because of the limitations of how memory management works in C++, and maybe because it lacks uh, things like algebraic data types? I mean, I see it used a lot. It's not all that
Um, uh,
intuitive, but
it's not as such that much intuitive, because using a type as a type, if I just want to typify something, like I want to say that this person is a male, this person is a female, I need to use a value, right? The moment you come into values, you have issues of how you represent it. Typically you will represent it using a string, then you have to convert that, have to do checks with that. You cannot have behavior with values and so on and so forth. So one of the styles that singleton fits in, that's why I said that there are two primary use of singleton as I see. There may be more. One is a real singleton scenario, like the railways. There is one railway, and therefore you will have one object. It does not make sense to be able to construct a second railway because everything will go haywire. But a singleton object can act for its type. So whenever we need that type, we can use that object. Because since there is only one object, and most often that will be created as a constant object, it can carry the whole behavior of the type with it. So I would say that it is a little bit more specific C++, coding style, design style. But in general, as you look into design pattern, singleton is a very well used thing, because there are several things which are singletons, and generalizations of that. For example, not every type is a singleton, but the types may have certain small number of specific values. So for example, say days of the week. Days of the week, there are 7 days of the week, right? There cannot be 6, there cannot be 8, right? So what is the modeling? If you just do day of the week and say these are the instantiations, then, well, there is always a possibility of a glitch that you could create more types of days of the week than actually exist. So we can get empowered to say that there is a concept called day of the week, and there are 7 specializations of that. Monday is a specialization, Tuesday is a specialization, and so on.
So, sir, we
And
need to do this because C++ does not have strong enums like Java does.
so because it does not have reflection. C++
also
does not have reflection.
True. Java does have
Right.
reflection.
So it has a reflection. So as we go into this object discussions more, we will talk about the third aspect of an object, which we have not touched yet. We have talked about 2 aspects of the object. The object has a state, it has a behavior, right? And we have not talked about the identity of an object. In a language like C++, the object does not have an identity. Its identity merely is its residence. Where does it reside in the memory? It has no semantics, right? So singleton singleton is a way to kind of give this identity when I need it as an identity. I'm not concerned about the state or the behavior so much. I just want the identity that this person is a male. I just want the identity that this person is a female. So that's kind of in something like Java, you could use a reflection to get some of that. But then again, it's all questions of modeling. How there are several ways you can model. Even in C, you did not have singleton or things like that, but you cannot easily implement singleton to the correct context. But still, that concept will exist, and the concept can be used. Right? So
yes, in C we have globals for the heavy use of globals.
yeah, and that is a disaster that we have.
True.
That is a disaster that we have, and that has caused so much of loss of productive manpower time. We are just trying to come to a formal model for doing this, so that it becomes very difficult to make an error, or errors can be caught at compile time. If I write male within quotes, it cannot be caught at compile times. But if I have 2 types of gender called male type and female type, then it simply will not compile if I give anything else, right? So that those kind of advantages you get. Oh, I'm sorry, you have crossed the time. Okay, so please, if you have more questions, keep it noted. Tomorrow when we start, you ask me those questions, and then we'll go on proceed with this further. Okay, thank you very much. Have a nice day. See you tomorrow morning.
Thank you, sir.